All right, let's dive right into this explainer because today we are looking at what is essentially a monumental mega engineering feat. We're going to explore the intricate architecture and the crazy training process behind the 535B A23B AI model, a project totally spearheaded by the Marin community. This isn't just your everyday software update. This is what the engineers actually call a hero run, a massive, highly coordinated launch of a cutting-edge open source project that is literally pushing the absolute limits of current hardware. It's a huge democratic win for the entire AI community. 535 billion, 300 million. Yeah, let that astronomical number sink in for a second. That represents the total parameter count of the model we're exploring today. In the AI world, you can think of parameters as the synaptic connections of the model's brain. So picture a massive digital rocket sitting on the launch pad, packed with over 500 billion of these connections, just waiting to be ignited by absolute mountains of data.
So, here is our flight plan for today's briefing. We're going to trace this colossal undertaking step by step. We've got Section 1, the payload, Section 2, the fuel, Section 3, the engine room, Section 4, the flight simulators, and finally, Section 5, mission control.
Let's kick things off with Section 1, the payload. Before this rocket attempts liftoff, we really need to inspect its structural design. The whole foundation of this model is built on a mixture of experts design, or MOE for short. If you want to understand how modern, massive AI models function without, melting down the world's power grids, you absolutely have to understand MOE. It's an architecture where only specific, specialized neural network layers, they call them experts, are activated for any given task. So rather than lighting up the entire model all at once just to answer a simple prompt, the model acts more like a super smart manager. It routes your specific query only to the exact experts best equipped to handle it. It's a completely crucial technique for managing this immense scale efficiently. And this right here perfectly illustrates that efficiency in action. While a rocket has a staggering 535.3 billion total parameters sitting in reserve, it actually only activates 22.76 billion parameters for any single token of text it processes. That is just incredible. It's basically getting the vast knowledge capacity and the deep nuance of a 500 billion parameter behemoth, but you're only paying the computing cost and speed of a much smaller 22 billion parameter model. That is a massive, massive win for efficiency. Moving right along to Section 2, the fuel. A digital rocket this massive requires an unfathomable amount of high-grade fuel to actually reach its destination, and in the AI world, that means data. The team engineered this incredibly rigorous decontamination pipeline to ensure the model only learned from the absolute best stuff out there. Step 1. They gathered a mind-boggling 25.6 trillion raw tokens from hundreds of different sources. Step 2. To stop the model from just memorizing repetitive garbage, they used min-hash fuzzy deduplication. That stripped out nearly 2.5 trillion duplicate tokens, basically ensuring the AI doesn't just read the same exact paragraphs over and over again. Step 3. This rigorous cleaning yielded a pristine, refined dataset of 23.1 trillion tokens. And finally, Step 4. They grouped all those documents into 40 distinct semantic quality buckets using a classifier called Harrier 0.6b. From this massive, highly organized pool, 18 trillion of those tokens are being fed directly into the model for this specific hero run. Now, let's step into Section 3, the engine room. Let's look at the custom hardware mechanics physically powering this whole operation. The sheer, uncompromising engineering ingenuity required here is just mind-blowing. Training this beast requires 11 KGB 200 NVL 72 server racks. But standard software? It couldn't handle the data traffic across that hardware efficiently. So the team literally hand-rolled their own pooled wave communication pipelines just to avoid digital traffic jams between the GPUs. They also implemented something called latent MOE, which effectively compresses the data, quite literally having the bytes moving across the network. And to keep the math from catastrophically blowing up mid-run, they added a logic Z-loss safety net and powered the learning process using a specialized muon-H optimizer. That optimizer uses a norm-preserving hyperbol projection. I know, that sounds like something straight out of Star Trek, but it's really just a mathematically beautiful way to keep the training totally stable. Every single one of these upgrades represents weeks of intense, headache-inducing problem solving. Next up is Section 4, the flight simulators. Okay, imagine footing the massive electricity and hardware bill for a 100-day supercomputer run. You would absolutely want to test your rocket in a flight simulator first, right? They didn't just guess that the final 535 billion parameter model was going to work out of the box. Instead, they ran progressively larger test rungs on what they call a scaling ladder. They started super small on a single rack with a tiny 61 million active parameter model. Then they scaled up step by step to a 1.2 billion active parameter rung across all 11 racks. By running these test rungs for just 1% of the total compute budget, the developers successfully caught explosive bugs early on, things like runaway training dynamics, and they mathematically mapped out their final performance trajectory. It was only after these simulator runs proved successful that they finally hit the big red button on the hero rung, scaling all the way up to the full 18 trillion tokens and 22.8 billion active parameters.
And that brings us to our final stop, Section 5, Mission Control. Once the Hero Run actually launches, Mission Control closely tracks its telemetry over the coming months. Which brings us to a really hard question right out of the gate. What if the hardware fails mid-run? Seriously, it is the ultimate nightmare scenario for any machine learning engineer. You're tens of millions of steps into a wildly expensive training run, and suddenly, compute nodes degrade, or a piece of hardware just completely gives out.
To prevent a total, devastating loss, the Marin community built in a highly strategic safety valve. Their buffer strategy dictates that if delays or failures start piling up beyond their allowed buffer, they'll mathematically compensate by shrinking the total token horizon by up to 25%. Basically, shrinking the token horizon means they're shortening the racetrack. And because the model's learning rate relies on a linear decay schedule to actually finish properly, they'll dynamically update that decay rate, essentially telling the model to speed up its learning so it can successfully cross the new finish line. This guarantees that even with a shortened track, the model is still going to land safely and hit its optimal peak performance without crashing and burning. But beyond just physical hardware failures, Mission Control is constantly monitoring the mathematical health of the parameters too. They save hourly checkpoints to ensure safety. But what's truly fascinating here is their optimizer tracking. They are basically watching the model's EKG in real time. They specifically monitor the data to ensure that those mu-on-H optimizer norms remain completely mathematically flat, exactly as that hyperbol projection designed them to be. Meanwhile, they're watching the standard atom parameters to make sure they evolve and grow exactly as intended. If those mu-on-H norms start drifting away from being flat, alarms go off immediately, signaling that the underlying math is breaking down. So where is all this mega engineering actually leading us? Well, based on those scaling ladder simulators we talked about, lead developer Classic Larry has predicted a highly specific final macro loss score of approximately 2.04. In AI training, a lower loss score basically translates to a smarter, more accurate model. Hitting a 2.04 proves the team isn't just blindly throwing compute at a wall and hoping something sticks. They have a very precise, mathematical expectation of exactly where this digital rocket is going to land. As we sit back and watch this astronomical 535 billion parameter rocket hurtle towards completion over its massive training cycle, it really leaves us with one profound question. What new frontiers will this open source behemoth unlock once it actually crosses the finish line? I mean, when anyone with a laptop can download the results of this brilliant engineering, what are you going to build with it? It is an incredibly exciting time to be following this space, and we'll certainly be watching the skies to see where this rocket lands.